Well, Yale, I do want to ask, what was the first ISCA you ever attended?
The first disco I ever
No.
attended.
Yeah, yeah,
I don't
the
remember.
Disco Symposium on Computer Architecture, right?
Oh, the first ISCA.
Yes.
Oh, I wasn't hearing you. The first ISCA I ever attended was in 1985, actually.
Uh-huh.
It was the one in Boston. In fact, that was my first ISCA paper, was the one in Boston, which was the Prolog machine that Aldo Spain and I built when I was teaching at Berkeley. And John Koch got the Mockley Award that year, who is one of the true giants in our field. Okay, what I want to do is make this, let's see, does that do it? No? How do I make this?
Oh, how do you make it present? Alt V and then W will typically make it a slideshow, or well, you're just resume your slideshow.
Well, no, that isn't doing it. Damn it. Well,
You're probably looking at a different screen, Yale. The one I see has this drop down that says slideshow in the upper left.
yeah, so I don't see no slideshow. Yeah, but do you see my title page or not?
We do, yes.
Okay.
But we see it, but we also see your you know, your stream of slides down to the left, which means that we're not watching the screen that you think you're displaying. It'll work this way, but
Oh, wait a
if you
minute.
can
So the
find,
little thing says slideshow. So
yes, just resume it and then you'll be fine.
do I want to click on slideshow?
You want to click on resume slideshow right there, right beneath the drop
Okay.
down. There,
And if I do that, what do you know? Good.
there you go.
I'd say you're as good as my freshman, Ed, as far as teaching me this technology. Okay, so now, because of my ineptitude, we're 2 minutes late getting started. Okay, so I should start it. Ed didn't say anything, or if he did, I didn't hear him.
Yes, start it.
Okay, so I should start it. Okay, let me get the laser pointer in case I need it. You see how great I did during our remote teaching with the pandemic. Okay, so this session is made up of 2 parts, thanks to the program committee. The papers, and then after that, a panel. And so I've titled the session Computer Architecture Education. Who should we teach? What should we teach? How should we teach it? And when should we teach it? Motivated by the papers submitted to the workshop, several papers focusing on their choice of ISA. One submission, which did not get accepted, unfortunately, said you don't need a computer, a nice embedded controller is plenty good enough. Unfortunately, there were a lot of problems with the embedded controller that they happened to pick, and so that paper was not accepted. But the point is that we could be as small as just an embedded controller. One submission suggested a professor invent his own ISA, which of course I also subscribe to. 2 submissions suggested using RISC-V. Because I've been around a while, I remember when Randy Bryant decided at Carnegie Mellon that he wanted to start with the x86. First ISA the kids learned, x86, which I thought was a nightmare, but he wanted it to be able to write operating systems code on a real machine. My personal choice is 2 ISAs, the LC3 for freshmen, the LC3B for seniors. Each of all of us have our own reason for the ISA. The result is we start with the 3 accepted papers, and then we follow this with a panel discussion. The ISA is the tip of the iceberg. What else is relevant? For example, what are the students that we're teaching interested in, and when are we going to teach them? And the panel will discuss each to the degree that you all wish. And of course, it's more than just a panel. Hopefully, the attendants will chime in much stronger than the panel. But first, the accepted papers. So the session is organized with, first of all, each of the three authors preparing a 3 to 5 minute lightning session. And when I shut up, Professors Kurtzinger and Weinman from Grinnell will start their paper. And then a paper from Professor Drzlinski and his students at Michigan. And then finally, Professor Sarah Harris, now at UNLV, and David Harris, still at Harvey Mudd. And then the rest of the session, hopefully more than 40 minutes, will be for the panel. And after that, the panel discussion. So I will unshare, I guess, and let Professor Kurtzinger and Weinman take over.
No, Charlie, we cannot hear you.
Also, you may be sharing the wrong screen. You're sharing a picture of Yale along with the chat.
All right, how about now? Is my microphone at least working?
Yes.
Okay, that's good. Now I have to share it and you all see Jared for a second here.
Unless you'd prefer to just look at me, which I guess.
All right, screen and microphone working?
It is for me, so.
All right, that's great. I don't have a view of comment, so if anyone does want to chime in, you'll have to unmute yourselves, but hopefully that doesn't happen during the lightning talk at least. So I'll be presenting PIPS, which is an instruction set architecture for teaching computer organization. As Yale mentioned, this is joint work with Jared Weinman, and we're at Grinnell College. So first, we should look at who's actually using PIPS. So we're introducing this in a course for computer science majors. Before we see these students, they've taken our first major course, CSC 151, where they will learn some functional programming in Racket. After that, they've taken 161, where they learn imperative programming in C. And then we get them in computer organization and architecture. So this could be second year students, sometimes it's seniors, but it's still potentially pretty early in the major. So PIPS itself appears in this course, and it's sandwiched in the middle. We start the class off introducing transistors, and we use those to build up to logic gates. Students use those logic gates to produce some larger circuits. And they do that using both physical circuits and with Logisim. At this point, we jump up to the other end of the stack, and we ask students to take concepts and ideas from C and translate those down to assembly. And then they do some practice translating assembly to machine code and thinking about how that encoding actually works. And they do that both with PIC32 microcontrollers and with the Mars simulator. To meet these in the middle and join them together, help students understand that full stack, we then ask them to complete a PIPS data path. So by the end of the lab sequence, we expect that students who've built the PIPS data path can devise the encodings for useful instructions they want to run on their data path. They understand the purpose of the connections between the components in the data path. They can determine the control line settings for their instructions, so they've thought about the control, not just the data flow. And they have a holistic view of the full system from assembly down to the data path components, and then they can jump from there all the way down to transistors if they want to eliminate any sense of mystery. So just some high-level details on PIPS. So it's a 16-bit ISA. We're using a 32-bit fixed-width instruction with just 2 instruction formats. There are 15 general purpose registers plus a 0 constant register. And this is all going to sound fairly familiar to many of you because the assembly language is very similar to MIPS. That's the instruction set that we're using for the rest of the class. And we borrowed instructions, syntax, register names, and calling conventions from MIPS. The machine code for PIPS is completely different though. It's been designed to simplify decoding and data path implementation. So we're not worried about compactness. We're not trying to be as expressive as possible. It's just meant to be quick and easy to use. Along with the actual data path, we ask students to implement an assembler for PIPS. And so as they're adding functionality to the data path, they're also writing the rules to translate assembly. We found that's a really useful piece of the lab sequence. So this is the Logisim circuit that we give to students at the start of the lab sequence. So as you can see, there's a program counter, instruction memory. There's a simple microprogram that students use to control different parts of the data path. The entirety of the instruction decoding is a series of splitters that you can see on the left there. They're provided with a register file and an ALU, but both of these are just slightly larger versions of circuits students have already built by the time they see these labs. And then the last bit is the memory controller and data memory. I'll just say the memory controller is just dealing with some headaches related with single byte accesses in a 16-bit architecture. There's nothing really sophisticated happening there. As far as the assembler goes, we give students some code that can assemble code, but it only has rules to translate 3 instructions: add I, add, and li, the load immediate pseudo instruction. And this is one of the ones that's provided to students. It's in Python, and students have to write more of these to translate more instructions. This first line here is just registering a syntax rule with the assembler. So students will be writing this for each new instruction they support. You can see that this looks for an add I followed by 3 parameters. That's what those pound signs are placeholders for. There's a Python function that's called anytime we encounter one of these. And those operands that match are passed in as parameters to the function. And then the third piece, they just use the pips module, which we've provided, to fill in the various fields of the instruction format that they choose. So they're not worried about the binary encoding and bit ordering and all of that. They're thinking about what goes in what part of the instruction. So we hand students those materials and we ask them to complete 6 pieces. This is roughly over 3 or 4 weeks. So at first, they're going to add some support to execute the actual instructions that are already handled by the assembler. They fill in the rest of the ALU instructions so they can do subtractions, some bitwise operations, that sort of thing. They add support for jump and link, and conditional branch instructions. They then add memory support. And at this point, there's a very simple mechanism for sending data to a terminal that's sort of a bare bones memory mapped IO. Students add support for bit shifting instructions and some useful pseudo instructions, which they use to write larger programs. And then finally, they handle memory map keyboard input at the tail end of this lab sequence. Once this is done, students write some larger programs that do interesting things with user input. We'll just take a look at a simple version of one of those now. So here you can see there's a pips assembly program that's going to look pretty familiar if you've ever written MIPS assembly. We could run it through the assembler, which has been completed. Open it up in Logisim, load it into instruction memory, and of course execute it. And you can see in the lower right here, the terminal is being printed to and the processor is actually executing the program. So just to wrap things up for the lightning talk, we found that implementing the full system stack has really helped students learn well. The vast majority of students successfully complete all 6 of the labs, so we think they're understanding it. And they give positive feedback on the lab sequence in their end of course evaluations. So we believe we've captured their attention. Using PIPS makes it possible to incorporate this full stack implementation into what's already a packed course. PIPS is really similar to MIPS, so students can learn it quickly, but they also get to learn that not everything is MIPS and they understand some of the differences between the 2 architectures. The simplified ISA also makes it easier for students to actually build the data path and not worry about some of the little headaches that come up with a more realistic ISA. All of the PIPS materials are available for use under a Creative Commons license. And most portions of the labs are checked by auto-graders, so we can provide those to you on request. So if you're interested in more details about PIPS or you want to see the full talk or read the paper, you can follow this link. And I'm happy to take questions during the panel discussion.
Okay, I don't know who's presenting from Michigan, but I'll just leave it open to you guys to jump in now.
Yeah, that'll be me, Steve Zecconi. Can you see my screen?
I do.
Okay, perfect. Yeah, so I'll just jump right in then. I'm Steve Zecconi. I am a PhD candidate at the University of Michigan, and I'm here to present our project, Teaching Out-of-Order Processor Design with the RISC-V ISA. So in the next couple minutes of this lightning talk, I want to try to talk about three things in particular. First is to give an overview of our CPU design elective course. And that's mostly to provide context for the second thing, which is talking about what students actually do in the course. They design a RISC-V out-of-order core from scratch. So it's a very ambitious project. They work really hard on it. And then the third part will be some justification for why we switched to RISC-V in this course. So the course itself is an introductory graduate level course on computer architecture. And the emphasis really is on designing out-of-order CPUs. The highlight of the course is for students to work in teams of 4 to 5 students designing their own CPU during the second half of the course. So in terms of who takes the course, we have about half undergraduates, half grad students from our program. We have about 50 to 80 students total any given semester, which is actually fairly small for our university these days, where we tend to have these mega classes of hundreds of students. And so it's nice because we have 1 faculty lecturer, 2 to 3 TAs. It's a good ratio of instructors to students, and we get to spend a lot of time working with the students, which we often don't in the introductory courses. The semester timeline loosely breaks down into a first half and a second half, which is dominated by this group project that happens almost entirely throughout the second half. So the first half is really all about teaching out-of-order algorithms and case studies during lecture and giving students individual projects to work on. They write these individual projects in System Verilog, designing different hardware components so that they have experience when they go to do the group project for the second half. Now, the group project itself, the goal is to design an out-of-order RISC-V 32-bit processor with a branch predictor and a level 1 cache. So the students work really hard on this because it's a really ambitious project. They work in these groups of 4 to 5 over 8 weeks. We updated the course to use RISC-V in fall 2019, and we used the RV32IM subset of instructions. So that's the integer and the multiply instructions, but not the divide, and no floating point. We keep it very simple, just about 40 opcodes total. The students write everything in System Verilog. It has to be synthesizable so that it can actually work when it's built into real hardware. That's a condition that we enforce. And then in terms of what they actually do and how they spend those 8 weeks, the first week or two tends to be getting used to working in their groups, designing one module and setting up their unit testing infrastructure. Then they spend about 3 weeks designing the core of their out-of-order pipeline. After that, they spend 2 weeks working on cache and memory. And the hope is that that leaves them with 1 week at the end to focus on debugging and optimization. And if that's not enough, they also add their choice of advanced features to try to boost performance to the base project. So very commonly, groups will add features such as superscalar execution. They will add cache features such as increased associativity, having a write-back cache. And we have a few groups every semester who do even more ambitious advanced features, like having an advanced branch predictor, or implementing multi-threading or multi-core designs. And so these are really cool designs. The students work really hard on it. It's always really neat to see what they come up with every semester. And unfortunately, because this is a lightning talk, we don't have enough time to get into details on this. We have more details in our video, or we're happy to talk to you if you're interested in some of this. Just ping us by email. So then, since I have about 1 minute left, I'll give our argument for RISC-V and why we switched to RISC-V. As most of you know, RISC-V is open source. It's been widely used in industry the past few years. The students, we find, are very enthusiastic about it because they get to use an ISA that they see in the news and that they can talk about at career fair with recruiters. And so it provides a modern perspective for them and builds their enthusiasm, which is great. RISC-V is also very simple and modular. It's a very elegant ISA, and that helps because I think, as Charlie made a good point in the last presentation, it gives students, it makes it easier for students to understand the full stack, which is really what we want. We want them to understand how software interacts with hardware. But all of those are good, but maybe not compelling enough to use RISC-V for a course like this. So it's really the last point here that's a distinguisher, which is the sort of software magic that RISC-V unlocks for us compared to using Alpha, which is we have a custom linker that allows us to use GCC, and we can actually compile arbitrary code that students write in C. They can compile it, I should say, into this RISC-V RV32IM code that can run on their projects. So that gives them access to all kinds of additional test cases and gives them additional ways to debug and helps make debugging easier for them. We can also emulate instructions. So something like a divide instruction, for example, that the students don't implement as part of the project can be emulated with a series of bitwise operations, for example. So that's really cool, and it provides us some interesting possibilities. So in conclusion, hopefully you've learned a little bit about what we do with this course. It's a very ambitious computer architecture design course. Our students work really hard to develop these cores. And we found that switching to RISC-V provided some really great tools for us to facilitate processor design and to help students really understand the full hardware software stack. So then I will just give a plug for the fact that we have a GitHub repo where we've open sourced our project and lab materials. And we don't necessarily have all the instructor solutions posted there because we don't want those to be public. So if you're interested in those, let us know. We're happy to chat with you and give you those. So thank you so much, and I will stop there.
Okay, Sarah?
Okay, can everyone see my screen and hear me? Can you hear me?
I can hear you.
Okay, great. Can people see my screen as well?
It looks black to me.
Okay, it's not good.
Looks back to you also.
Pause it. Try it again. How's that?
There you go.
Okay, perfect. Okay, I am Sarah Harris. I'm an associate professor at the University of Nevada, Las Vegas, and my co-author is David Harris. He's a professor at Harvey Mudd College, and this talk is about a textbook that we're almost done with called Digital Design and Computer Architecture, RISC-V edition. So we've adapted our other digital design computer architecture textbooks to focus on RISC-V. So the other two, the first edition, the first book was focusing on MIPS architecture. Second edition was in 2012, and the next one was on the ARM architecture. And so the expected publication date of this new one is just in a few months on August 15th. So some statistics about the success of these books so far. Last year, in 2020, the publisher said that 10,000 university students used our other two textbooks. They don't track the international use, but it's available in 7 languages. And it can be taught as either a 1-semester course, as it's done at Harvey Mudd, or a 2-semester course at UNLV, or for example, in a university in Germany that I taught at as well. And as David and talked about in an earlier session, we've also developed a MOOC to go along with the textbook. So I think Steve covered this pretty well. Why RISC-V? Open source, it's commercially viable, has a lot of flexibility, and it's reasonably simple, and so students can understand it pretty readily. And so we could go over this. I'll just leave this slide as something you can read. But basically, it's very similar to MIPS, but gets rid of some of the idiosyncrasies, and it's used in commercial products. ARM, the big thing behind that one is it doesn't require the licensing and kind of gets rid of some of the complexity as well. So, so we build up from, binary numbers and logic gates up through, more complex digital circuits such as adders and dividers. And then we, I guess similar to Steve's kind of trajectory in his course, then we jump up to C programming, which is actually an appendix. It's optional. And then down into RISC-V architecture, assembly programming, instructions, machine code, and finally back down where chapter 7 really brings it all together, talking about how do you build this using all of those building blocks that you talked about in the first half of the course. And so there really is, there's no black box in this. And that's kind of the beauty of it, is that students understand every level that they're using and building and designing with. So we talk about 3 different processors, kind of increasing in complexity: single cycle, multi-cycle, and pipeline. And we build a subset of instructions, and in the exercises, guide the users or guide the students in expanding the processor. And so here's a picture of the single cycle processor. And again, the students understand every single one of these building blocks and have built some in the labs. Multi-cycle RISC-V processor, and then the pipeline processor, which is based on the single cycle they built in one of the labs. And so for the labs, we use free software. So the course, it can be taught without cost. There's optional hardware, which we like. A hands-on learning is, it's really nice to actually see the LED blink instead of just see the signal go up in simulation. But if cost is an issue, certainly this is you can just do everything in simulation. And also the hardware, we target the D2-115 board, but if your university happens to have different FPGA boards, readily adaptable to those as well. And here's a picture of the hardware. We use the Red 5 Red board, which is a microcontroller based on a RISC-V processor, and a list of labs. So we start with schematic entry because we find that if you go straight to System Verilog, people are thinking in programming languages and it's a mess. And so if they can start helping the students think in hardware, what hardware will this generate? It really gets rid of a lot of the latches and other issues with kind of thinking of System Verilog as a programming language instead of a hardware description language. And then we jump up to C programming. We actually have some optional assembly programming labs as well, and then back to System Verilog for building the processors. So in conclusion, we've written a textbook, and we have companion material, including exercises, exercise solutions, labs, slides, etc., that builds up to designing a RISC-V processor from the ground up. And we find that teaching these together, we've been doing this for about 15 years, really enhances their student understanding of both topics, both digital design and computer architecture. And so, really kind of combining them is more than the whole, more than the parts, right? I would like to thank especially our colleague Josh Brake, who's also at Harvey Mudd, who contributed to chapter 9, and a bunch of reviewers for our textbook. That's it. Thanks.
Okay, so now I introduce the panel, and let's see. I guess I want this. Good. Okay, you can all hear me okay? Yes, no?
Yeah, yes, but I don't see anything on the screen.
You don't see anything on the screen. Okay, so what I see, okay, so I don't know what my problem is. I see on the screen, but
Are you share? Did you hit share screen?
I thought so how do I get out? Here we go, escape. Okay, now you don't see anything on the screen, huh?
Not yet.
Okay. Let me get rid of this. Let me hit share screen. Okay, let me hit this. Let me hit share screen. Okay.
There you go.
Okay, you see it now, yes?
Mhm.
Okay, now I need to,
Hit slideshow.
I
Go
don't
to
see, I don't see,
Slideshow right over, you're just past slideshow.
I did. Here we go.
Yeah, there. Okay. And now you hit from current slide. It's over the second one from the left.
Second one from current slide, okay?
Yeah,
Okay, now you can see it, huh?
yes.
Okay, so I need to back out. Okay, good. Thank you for tutoring me. Okay, so the panel discussion. So questions, who should we teach? That's my first question. Should every student understand how a computer works? Or should it be only those students who care about computer architecture? What should we teach? Caches, virtual memory out of order? What about these new sexy things, machine learning, quantum? What should the ISA be? A commercial ISA, or should the professor invent one? When should we teach it? Junior, senior year? Steve mentioned it's a graduate course. I'm kind of curious to know more about that graduate course. I'm wondering if that was the CS 470 that I introduced when I taught at Michigan. Because
Yep, that's the one.
really, and they're able to
Yep.
do all of that in 8 weeks. I am impressed.
Yes,
Michigan
yes.
students have gotten much better since I was there. I can't even conceive getting all that
Well,
done in 8 weeks.
Yeah, the tools have gotten better too, I think.
Ah,
But
the
yes.
tools, I hate tools. Tools get in the
Yeah.
way. They create magic, is what tools do. So my 2 cents, there are 2 distinct groups of computer science and engineering students. Those that could care less about how computers work, but still need to know it, and those who are serious about computer architecture. I call the first group Group A, and for them, I suggest a fundamentals course, not really computer architecture, teach it in the freshman year, so no caches, no virtual memory, no pipelining, but they do see a cycle by cycle implementation of a simple ISA. Students are actually able to debug their own programs. They write the programs in either zeros and ones or assembly code, and then translate it into machine code, and then run it on the simulator, single step debug, etc. And they can actually write and debug programs without having the TA do it for them. I'm tired of CS graduates graduating without ever having actually written a program by themselves. And the freshman year, they start their college education with a strong foundation, which that provides. For Group B, the serious students, lectures, problem sets cover all the normal stuff. I'll get to that. And a lab component, which implements a complete ISA, data path, finite state machine, microsequencer, the entire instruction set, but it's a simple instruction set, and I'll get to that. Okay, so if the freshman course is not computer architecture, why am I talking about it at this workshop? A, because it provides an important foundation for all students. We are the best equipped to teach it. We are the best to recognize its value. And most importantly, if we don't push it, it's not going to happen, and students will miss starting out with a very strong foundation. The LC3 is very much like the PIPS instruction set, near as I can tell. 8 registers, NZ and P condition codes. As you all know, P is redundant, but if I include a P condition code, then the code the students write gets less ugly because you've got a duality property that you're not, pulling out your hair trying to get the conditional branches to work properly. 16-bit address space, only 3 addressing modes: PC plus offset, register offset, and indirect. Why indirect? Since nobody does indirect anymore, because freshmen have problems with pointer variables. Indirect says load register 1 and gives you the label A. A is an address of a location in memory that contains the address of the data. And so the kids get to understand pointers without even realizing it. We do have privileged memory, both kernel and user, and memory mapped out. Memory mapped IO. We left out all the bells and whistles, even endianness, because instead of byte addressable, it's word addressable. So I don't have to worry about endianness. An instruction occupies one location in memory. 15 opcodes. So we have a textbook, and the adopters push me to add, multiply, shift, add, carry, and we've resisted that, keeping it simple. Here's the entire instruction set, 15 opcodes. Only one arithmetic, add. If you want to subtract, you get the complement. So you want to do A minus B, get the negative of B and then add. You want to multiply, add. Two relationals, not an and. People have suggested one relational, NAND. I've ignored that because NAND is not quite so intuitive as not an add. You have conditional branches, subroutine call, and return from interrupts because the kids write their own interrupt handler. And also a trap instruction, which is a system call. So in the beginning, before they understand how physical IO works, they trap to the operating system to do the physical IO for them. By the time the course is over, they're writing their own physical IO with data and status registers associated with each IO device. Here's the entire data path. I was delighted to listen to the lightning sessions that everybody seems to now agree. That wasn't the case when I started out. Now, apparently, we have won this one. We start with transistors and keep building and building and building, removing more and more magic, raising the level of abstraction. And so by the time they get to this data path, they already know how to do all these pieces you see. They built muxes, they've built a finite state machine, they've built registers, etc. Down the bottom, you see the memory mapped IO. So you've got a memory address register, which either points to memory or one of the device registers, and two devices, a keyboard and a monitor. And they both have data and status registers. When somebody hits a key, it puts the ASCII code into the data register and sets the ready bit, which can then be interrogated on the program control, or it can be interrupted if the interrupt enable bit in the status register is set. Here's the finite state machine. The kids actually go through cycle by cycle. In fact, I was interested to see the Sarah's talk of a single cycle, which I guess is good for first level understanding, then multi-cycle, and then pipeline. We don't do pipelining in the freshman course, but we do multi-cycle so that every clock cycle, they see what control signals are needed. Then the senior course, we added virtual memory. The NOT became the exclusive OR, retaining compatibility because A, exclusive OR 1 is not A. Word addressing added byte addressing because most memories are byte addressable. By the time they get to be seniors, they need to know that all memory is byte addressable pretty much. And we got rid of load indirect and store indirect because if they stood on understand pointers, by the time they get to be seniors, they have a bigger problem than computer architecture. And we added a comprehensive shift instruction. The senior course, the lectures emphasize concepts, and you can see them all: physical memory, virtual memory, process state, exceptions, pipelining, branch prediction, out of order, cache coherence, memory consistency, all the stuff that you'd expect to find in a serious computer architecture course, which is for people who really care about computer architecture. But I also insist that an important component of a senior course is implementing a instruction set architecture. For that, the LC3B, which is a byte addressable LC3 with those added features I mentioned. We provide them in Lab 2, the control signals, the data path, the state machine, the microsequencer. They come up with when do they use each control signal in each clock cycle. And then after that, they add their own state to the state machine functionality to the data path and control signals to the microsequencer to interrupt, to implement, first of all, exception and interrupt handling, and then virtual memory. And then we throw it all away and do a pipeline design. And the pipeline design looks a lot like the slide that Sarah showed for her pipeline design. And finally, in my view, black boxes is magic. I guess based on the earlier talks in the session, I don't have to convince anybody of that. Everybody now seems to agree, which I'm delighted. Magic impedes fundamental understanding, and lack of understanding limits how high you can actually go, and that is harmful. Thank you. Okay, so now I should stop sharing and throw it open. First of all, so I am not going to act like a monitor. I'll let people jump in when they see a lull and just ask questions or talk or comment or whatever. And first I'll invite the other panelists, the other speakers to interject with their questions or comments of each of us, and then we'll throw it open to the whole audience. Okay, fire away.
So if I can dare to get things started, I want to thank all of the other speakers today for their interesting work. And I actually wanted to ask a question of David and Sarah about their approach. So I should say I am not an architect person by training. I teach at a liberal arts college and get to teach in many things outside of my experience. So I could very well be converted to RISC-V or RISC-V. I think it's you all make some really interesting and compelling arguments. One of the things that Charlie and I said in the paper about PIPS is that because we force students to think about a different architecture where they really have to construct the control lines and or the control signals and build it together, it really forces them to understand things. So I'm wondering, as you ask students, say, to build a R32I, if I have that right, I don't know what's in your textbook, obviously, because I haven't seen it. But if one could imagine that they're just kind of following along what the diagrams say to do without really understanding necessarily why things need to be that way or why the ISA or the control signals were designed that way. So I'm wondering if you share this sympathy or perhaps the opportunity that something like PIPS offers, and maybe how you get around that, if you even see it as an issue in that sort of middle ground where you're trying to help students understand what's going on, but also why.
No, Sarah, before you answer, I have one question for Kurt, for Jared and Kurt, that I'd like to know. And that is your PIPS a single cycle simulator, or do they go clock cycle by clock cycle? That is, in one cycle, do they fetch, decode the instructions, send it to memory, get the data, and load it into a register? Or do they do cycle by clock cycle by clock cycle?
It is a single cycle data path. They see pipelining, but we found that implementing it complicated things enough that we couldn't do some of the other sort of elimination of black boxes in the class we wanted. So yeah, it's single cycle in terms of what they build.
Sarah, I'll let you answer.
So that's a great question about implementing instructions and really understanding them. And our book walks through implementing a subset of the RISC-V architecture, the essential instructions to write real interesting programs. And then it adds a few more instructions showing how you add new instructions to the processor. And then in the exercises, the students add additional instructions. So the instruction set is rich enough, there are plenty more to choose from. They get to do this on the homework, and they get to do it in the lab. And then on the final exam, there's always another instruction for them to add to the processor. So that way, that way we make sure that they aren't just repeating what was in the book, but they understand it well enough to enhance it.
And to add to that, we don't just give them the schematic diagram, right? We build it up by, okay, so how do we, right? You start with an instruction, the load word instruction, and we say, what do you need to implement that, right? And so it's piece by piece, but they actually, it's kind of this interactive, well, I guess we need a register to hold the program counter. And so they build it up, both, the base processor, and then, as David said, they expand it themselves. So they can't, if they don't, you're right, if they might not have completely they might have just followed the process, the design process, but that design process really is the core of it. Not, hey, here's the end product, but it's that process of design that really is the point.
Any of the other panelists have something first? Stephen, I'm still struggling with this notion of what these guys and women have been able to accomplish in 8 weeks. Is this actually their first introduction to how the computer works, or is there an earlier course?
Yeah, no, I should have made that clear. This is an elective course. They have a required course. We have a required course, I should say, for computer science majors that they typically take in the second year as majors. So it's a bit like the freshman course that you were talking about in terms of depth, although they do cover.
Is this 370?
Yeah. It's
Yeah,
370.
okay. So what I did when I was at Michigan is I moved 370 into the freshman year. And
right.
So this 470 then became a senior graduate course. And even with all that, I'm impressed that they can, in fact, I find it almost impossible to believe, but so we'll get together maybe offline and so you can convince me. This is
Sure. Happy to talk about it. It is very impressive what the students are able to do. And I think the bar keeps getting raised one semester after another. And so students are always eager to prove themselves. And so they try to outdo what was done before. And it's very impressive. So, yeah.
Other comments or questions?
On that follow-up,
Sorry.
Stephen, I agree. That's really remarkable what your students do. We've taught a similar course for undergraduates, building this RISC-V processor, full pipeline processor this spring. And we found we got hung up for several weeks debugging things related to stalls and the interaction with external memory bus. There are just a lot of nasty corner cases that take a long time to track down. And I'm curious what you do if you provide any sort of scaffolding or some successful models that you found that help your students avoid getting caught in these rat holes. And also what kinds of bugs your students do spend the most time resolving.
Yeah, that's a great question. So we do a couple of things. One thing is we've been really lucky that the instructors tend to remain the same semester to semester, and a lot of the lead faculty instructors have done this course several times. Some of them even took it as grad students. And so they have experience knowing what it's like being in the trenches to develop these processors. And then we do provide students with a fully functional pipeline processor that they can use to debug. And so that helps with debugging substantially because they can get a final memory output of running any arbitrary program and know that that's the output that they should get. And then they can go back and retrace what the register values were as that program was executing. And once they develop that as a kind of technique that they can do, then debugging becomes much faster. And then it just becomes debugging their own code. And of course, it's easiest to debug code that you wrote. And so that tends to maybe not be easy, but at least they can start to narrow things down that way. And so I think really providing them that reference design of an in-order pipeline processor helps them debug a lot faster. It helps them avoid some of the crazy corner cases that you could imagine happening. So we also give them a bunch of reference programs too. So we give them tons of test programs that they can work with, and they start from very simple to very, very complex. So, yeah.
Okay, I want to throw it open to everybody else. So anybody want to comment, questions, whatever for anybody?
There's a question in the chat that I thought was kind of interesting about how much are students retaining. There's a lot of details we could give them. What's actually durable over time. For my part, I would say I don't have a concrete answer to that because we don't do exit testing at the end of the degree. And do I think that they know how to design an AND gate from transistors, even though we taught that at week 1? Probably not anymore. But I think the really important lessons that we hope computer scientists, rather than computer engineers in our context, should learn. I'm optimistic that they do, that they have a really perhaps basic but concrete understanding about how the computer executes their code. And that stems from their exploration of actual implementation and tracing. But I'm interested to hear others' opinions as well.
So I can anecdotally tell you that every year I get about a dozen emails from students that I had 10, 15, 20, 25 years ago, thanking me for the freshman course, because they say that foundation that was laid is still useful to them in their work, many, many years later. And so in fact, this past month, I got 2 letters from Michigan students that I had in class in the 90s. So I don't know how much of the actual detail is retained, but my guess is a lot more than we think. Question, comment?
So I can provide some input to that. By the way, this is Tan from Michigan. That as for our class goes, I think most people retain, if not, the most is probably their RTL coding skills just from implementing a project. They get a lot of hands-on experience. If you ask them how much RISC-V or, back in the days, alpha experience they retain, right? Well, one, it's not the biggest highlight of the class. We don't cover it that excessively. I think the idea is just that they get a basic sense of, what is in an ISA. Well, they probably have that from previous classes already. But I think whatever is the most hands-on is what they will understand the most. So in their case, definitely a lot of RTL coding and just all the how out of order pipeline looks like. But in terms of other more more abstract things, it's hard to say.
No question that what they do hands-on will be the thing they retain most. I guess we've seen a lot of experience with that.
It's not all, it's also not what they know off the top of their head, right? It's what can they spin up on in 15 to 30 minutes. So you might hand them a test and they might kind of get wide-eyed, but if you give them 15 minutes to think back on it, can they get up and going as opposed to having to take another week to learn it again from scratch?
Questions, comments?
So yeah, I'll get a little bit of a debate going here. I'll put out a premise that we should teach with real architectures and real tools unless there's a compelling pedagogical reason to do otherwise. And the challenge here is, what are the pedagogical issues that lead us away from using commercial architectures and mainstream tools?
So my response is back to this magic thing, and I'd have to really get more deeply into what you're doing to really be able to speak coherently about it. But when I see names of software packages that help, I'm not a fan of that. With the LC3B, they can write code. They have an interrupt enable bit that they can interrupt the program that's running, interrupt to an interrupt handler, and then return back to back to the code. Everything is concrete, and that I think. So, I guess the claim is that there's nothing in RISC-V that's not concrete, and if that's true, then I need to examine that more closely. But my experience has been that when you start adding these things, in fact, I've had instructors that want to teach the freshman course, And before you know it, they've added all these software packages to help them understand the LC3. And the LC3 is a very simple machine. They don't need all those software packages. If you're telling me that you don't really have software packages, then, you know, I was misguided by some of Sarah's slides. What is compelling is to remove magic. And my answer to that, and I guess I should plug the textbook, which is, I finally got around to writing the 3rd edition after the prodding for everybody, and that's available. Far too expensive from McGraw-Hill. So if you can borrow one, I'd recommend it. But it's simple enough, and they get their hands dirty, and they actually make the whole thing work. If you tell me you can do that with RISC-V, then I don't know. Maybe I don't have a leg to stand on. I guess I need to see that more. I did, by the way, ask a couple of students at Texas who did their capstone senior design by implementing the basic RISC-V and then adding some accelerators to speed up certain functions that they wanted to speed up in hardware. And so they had the benefit of the LC3 and LC3B, and then they moved to RISC-V. And I said, well, how would it be if we replaced the LC3 with the RISC-V, you know, just a basic subset of the RISC-V in the freshman course? Would that be a win or a lose? And their response was it would be a lose. So I need to dig further, but I'm absolutely willing to have that debate.
I would love to hear specifics because when we talk about software packages we use are things like GCC, which I think are inherently good for students to have some exposure to a mainstream compiler, for instance. But I'd be very interested to hear if there's anything in the simplified RISC-V microarchitecture that is not in LC3 and that could be stripped out to make the architecture any more approachable for students.
How many instructions in the RISC-V basic set? How many
So we
opcodes?
have, let's see, add, subtract, and or, add immediate, branch, load, and store.
And that's it.
That's the fundamental, yes.
Yeah, so you don't have a subroutine call?
We add jump and link later on. It's part of the
You don't have a system call. Yeah, I guess you don't need a system call. Are you doing I/O, physical I/O?
We do
How do you
memory
do
mapped
I/O? Let me ask it that way.
memory mapped I/O.
I understand that. So the student actually writes the instruction, load register 1 from a memory, from a data register, which has an address.
Yes.
So okay, so the I/O is done instruction by instruction.
By the time we get to that point in the course, we've gotten to C, and students understand pointers. So they define a pointer to the memory mapped I/O and access it that way. So they understand how that reduces to assembly.
Okay, and before you get to that, there is no I/O?
Correct.
Yeah, okay, so I introduce I/O pretty early as a system call, and then the operating system does it all for them, but by the time the semester is over, they've actually written their own system, those procedures to do the I/O, which is to spin on the ready bit of the status register until somebody hits a key and then load it into register 0, which is the register we use by convention with the operating system. So, as I say, I need to dig deeper with you, and Did you say there's a conditional branch?
Yes, there is.
I guess I just need to look further.
We'll have to talk about it over lunch sometime.
Then we will have that debate. And by the way, I'm impressed with the beard. My beard has gotten shorter and you've grown one since the last time I saw you. Other comments?
And I'm impressed with the session, but the time is up and we'll have to take another break. So let's take a break of 7 or 8 minutes and start a couple minutes after the scheduled starting time for the embedded session, which is the second last of the workshop. Thank you,
Okay.
everybody.
Thank you, Ed. Sorry I was too sloppy with keeping track of the time.
Okay, it's fine. It's fine. We're doing okay. We're within 2 minutes of being on time.
Great. Okay, session's over.